In this video, we're going to talk about the central limit theorem. So what is the central limit theorem? The basic idea behind the central limit theorem is this. Let's say we collect samples of size n from a population, and then we calculate the mean of each of those samples, and then plot those means on a histogram. The histogram will approximate a normal distribution. So imagine if, let's say you have 100,000 people in a town, and you choose a sample of 30 individuals, and then you calculate, let's say, the mean of sample 1. Let's say you calculate the mean age of the 30 individuals in a sample. Let's say it's 41.8. And then you calculate the mean of another set of 30 individuals. Let's say it's 39.6. And then you take another sample of 30 people. You calculate their mean age. Let's say it's 40.5. And then you repeat this process. And then if you take all of these means and plot it on a graph, the graph will have the shape of a normal distribution. Even if the graph of the population, which we don't know, even if it's not normal, this graph, where we plot all of the sample means, or the means of each sample, so this will be x bar, it will have the shape of a normal distribution. So that's the gist of the central limit theorem. If the sample size is large enough, the sample distribution taken from any population distribution, regardless of its shape, will approximate a normal distribution. A good value is if n is equal to or greater than 30. So let me illustrate that with some examples. So on the left, I'm going to put the population distribution. And on the right, I'm going to draw the shape of the sampling distribution. So for our first example, let's say that the population distribution has the shape of a normal distribution with mean mu and a random variable x. Now, if we collect samples out of this population and calculate the means of those samples and then plot it on a graph, we're going to create a new distribution called the sampling distribution, but specifically the sampling distribution of the sample means, because we calculated the mean of each sample taken from the population. So thus this is going to be x bar, because we're plotting the means of each sample on this graph. X represents the individual observation of the population. X bar represents the mean of a sample collected from the population. So make sure you understand the difference between the two. So since the population distribution had the shape of a normal distribution, the sampling distribution will also have the same shape, but for this case, for any n value. The reason why it's for any n value is because the population distribution already has the shape of a normal distribution. But now, what if the population distribution had a different shape? Let's say if it had the shape of a uniform distribution, or if it had the shape of an exponential distribution, or if it had the shape of just some unusual distribution. If we collect samples from the population, calculate the mean of those samples, and plot it on a graph, we're going to have the sampling distribution of the sample means. And if n is large enough, if n, let's say it's greater than or equal to 30, then the sampling distribution will approximate a normal distribution. So in this case, if the population distribution has a shape other than a normal distribution, you need to collect samples with a large enough size, 30 or more. Now, for those of you who are wondering what a sampling distribution of the sample means is, it's simply a probability distribution where the sample mean is plotted on the x-axis. Now, since the sampling distribution approximates the shape of a normal distribution according to the central limit theorem, we could use the z-table to make some probability calculations. So let's say if we wish to calculate the probability that a sample taken from the population is somewhere between A and B on this graph, we could use the z-tables to get the area under the curve and thus the probability that the sample mean is between A and B. Now let's talk about some symbols and variables that you need to know. So mu, this is the population mean. You've seen that before. The next one is x bar. This is the mean of the sample, or you could say the sample mean for short. Next, we have mu with a subscript x bar. So this is the mean of the sampling distribution. Next is sigma. This is the standard deviation of the population. S represents the standard deviation of the sampling. I take that back. It's the standard deviation of the sample, not the sampling distribution. Sigma with an x bar as a subscript, that is the standard deviation of the sampling distribution. So notice the difference between S and sigma sub x bar. S is just the standard deviation of a single sample. Sigma sub x bar, that's the standard deviation of many samples, of a sampling distribution. So here you have just one sample, and here you have many samples, an infinite number of samples. So notice the difference. Lastly is n. N is just the size of the sample. Now the next topic that we need to talk about is the law of large numbers. And the basic idea behind the law of large numbers is that, in reference to the topic that we're talking about, let's say we take a sample. If we increase the size of that sample, the mean of the sample will get closer and closer to the mean of the population as n increases. So let's say if the average age in a certain town is 36, so that's the population mean. But now let's say there's 100,000 people in that town. In order to get this answer, you don't want to calculate you don't want to ask 100,000 people, hey, what's your age, to calculate this number. Instead, what you want to do is you want to take small samples and calculate the mean of those samples to estimate this number. So let's say the first sample that you take has, let's say 10 individuals, and you calculate the mean or the average age of those 10 individuals. So let's say you get 32. The next sample, let's say you ask 50 people for their age, and you calculate the mean of that sample. Let's call this sample 2. Let's say you get 38.5 as the average age. Next, let's say in your third sample, you average the ages of 100 individuals. Your answer will get closer to the true answer. So let's say this one will be 35.3. And then finally, you throw the long ball, ask 1,000 people, and you get a mean of 36.1. Notice that as n increases, x bar gets closer and closer to the actual mean of the population. And that's the basic idea behind the law of large numbers. Because if you have a small sample, an extreme or an outlier may greatly affect your mean. So if you ask one person who's like 100 years old, this will greatly affect the average. Or if you ask a baby who's like less than 1 year old, it's going to affect the average big time. But the basic idea behind the law of large numbers is that as n goes up, the mean of the sample gets closer and closer to the population mean. Now let's think about this. If the mean of one sample can approximate the population mean if that sample is large enough, what about many samples? Well, the same will be true according to the law of large numbers. As n increases, the mean of the sampling distribution will approximate or get very close to the population mean. So if n is large enough, let's say if n is 30 or more, the mean of the sampling distribution is basically equal, you can say approximately equal to the population mean. Now, this is important to note because when we need to calculate z, this will affect the equation. You've seen this equation for a normal distribution. Z is equal to the random variable x minus the population mean divided by the population standard deviation. In the case of a sampling distribution, z is going to be x bar minus the the mean of the sampling distribution divided by the standard deviation of the sampling distribution. Now, the standard deviation of the sampling distribution is the standard deviation of the population divided by the square root of n. And when n is large, we can replace the mean of the sampling distribution with the mean of the population. So we get this equation. We can calculate z using this formula, x bar minus the population mean divided by the population standard deviation over the square root of n. So if n is large enough, when the sampling distribution approximates a normal distribution, you can do your probability calculations using this formula by calculating z and then using the z tables. Now let's talk about the effect that the size of the sample has on the shape of the sampling distribution. So here's a question for you. If we increase the size of the sample, what effect does it have on the standard deviation of the sampling distribution? Will it go up or down? Now we said that the standard deviation, I need to make sure I'm writing sigma instead of theta. We said that the standard deviation of the sampling distribution is equal to the population standard deviation divided by the square root of n. Now notice that n is in the denominator of this fraction. Whenever you increase the value of the denominator, the value of the fraction goes down. So what we have here is an inverse relationship. By the way, the standard deviation of the sample means, or the standard deviation of the sample distribution, it's also called the standard error. So notice that as n increases, the standard error decreases. So if the error is less, the accuracy is better. What this means is that the shape of the graph becomes more narrow. The data will be less spread in the sampling distribution. So let's say if n is 10, the sampling distribution will have a very wide shape. It may look something like this. It's going to be short and wide. Let's say if n is 30, it's going to be taller and more narrow. If n is 50, it's going to be even taller and even more narrow. So this has the longest spread and therefore the greatest error. And this one has the shortest spread and therefore the lowest error. So the standard error, or the standard deviation of the sample mean, is going to be the lowest when n is the greatest. So just keep that in mind. As the sample size increases, the standard deviation of the sample means will decrease, causing the graph to have a more narrow and taller shape. Now, before we go over some practice problems, it might be good to review some formulas that you need to know in order to solve these practice problems. So first, let's do a brief review of the uniform distribution. If you recall, the uniform distribution has a shape that looks like this. The height of the rectangle is basically f of x. F of x is a constant value. F of x is the probability density function, and in this case it's equal to 1 over b minus a. X is restricted between a and b. The distribution can be written this way. We have the random variable x, and we have a uniform distribution which varies from a to b. A is the minimum value, b is the maximum value. The mean of the uniform distribution is the average of a and b. So it's the sum of a and b divided by 2. The standard deviation is the difference between b and a divided by the square root of 12. So when dealing with any problem involving the uniform distribution, these are some formulas that you need to know. And keep in mind, the probability is equal to the area under the curve. So the area is a rectangle. The area of the rectangle is equal to the length times the width, or you could say the base times the height. So let's say if you want to calculate the probability that x is between c and d. The base of that rectangle is b. So that's the difference between d and c. The height is simply f of x. So the area of that region is going to be the base, which is d minus c, times the height, which is f of x, or 1 over b minus a. So it becomes d minus c divided by b minus a. So those are some things that you need to know when dealing with the uniform distribution. Now let's move on to the exponential distribution. Let's spend a few minutes reviewing the formulas associated with this. So the exponential distribution has a graph that starts at the y-intercept. The y-intercept is basically the maximum value on the y-axis, and at that point that's equal to lambda, which is the rate parameter. The function f of x is the probability density function, and it's equal to lambda e raised to the negative lambda times x. Lambda, the rate parameter, is 1 divided by the mean, and the mean is equal to the standard deviation for an exponential distribution. Now let's say if we want to calculate the probability that x is less than a. So this is equal to the area of the shaded region on the left. The area to the left is also known as, the formula that gives you the area to the left is known as the CDF, the cumulative distribution function. And in this case, you could use this formula to get it. The probability that x is less than x, in this case that would be x is less than a. This is equal to 1 minus e raised to the negative lambda times x. If you wish to calculate the area to the right, which will be the probability that x is greater than x, this is going to be e to the negative lambda times x. Now let's say if you want to calculate the probability that x is between b and c. In this case, you need to use this expression. The probability that x is between b and c is simply the difference of the probability that x is less than c, but minus the probability that x is less than b. Now let's go over some formulas that you need to know when dealing with the normal distribution and the sampling distribution. I'm going to put these two together so you could compare and see the difference. So here's a typical shape of the normal distribution. It has the population mean mu and the random variable x. The sampling distribution, if n is large enough, will have the same shape approximately, but with the standard deviation of the sample means. That's mu x bar. And on the x-axis, instead of x, it's going to be x bar, the means of each sample. Now to write the distribution, for normal distribution, we have the random variable x, n for normal distribution, population mean mu, and the standard deviation sigma. Now for the sampling distribution, we can write it this way. Instead of x, it's going to be x bar. It's still the shape of a normal distribution with the mean mu. Now keep in mind, when n is large enough, these two are approximately the same. So you can just write mu instead of mu x bar. So the mean is going to be the same, mu. And then this is going to be, now, so the standard deviation of the sampling distribution is sigma divided by the square root of n. So we're not going to have sigma here, but we're going to have sigma over the square root of n in this area. So notice the difference. X bar instead of x, and then sigma over square root n divided by, instead of just sigma. Now let's say if we want to calculate the probability that x is less than a. To do that, we need to calculate the probability that z is less than x minus mu over the standard deviation if we have a normal distribution. Now for a sampling distribution, let's say we want to do the same thing. The probability that x is less than a for the sampling distribution is going to be the probability that z is less than x bar, the sample mean, minus mu, the population mean, divided by sigma over the square root of n. So when calculating the z-score for normal distribution, you could use this formula. And when calculating the z-score when dealing with a sampling distribution, where you have a sample of size n, where n is not 1, you would use that formula to calculate the z-score, and then use the z-table to get the area under the curve, which will give you the probability. So those are the formulas that you'll need for the problems that are coming up soon. So here is the first problem. Number 1. The entrance exam scores of a certain university has a mean of 74 and a standard deviation of 6.8. The exam scores follow a normal distribution. Part A. If a student is selected at random, what is the probability that his exam score is less than 65? So let's write down what we know. We know the mean is 74. The standard deviation is 6.8. And we're dealing with just one student, so n is 1. Now, if we were to draw a graph, we're dealing with a probability distribution that has the shape of a normal distribution. So this is going to be x instead of x bar with the mean mu. Now, we want to calculate the probability that his exam scores is less than 65. 65 is going to be to the left of the mean. So we need to calculate the area under the curve to the left of 65. So the probability that x is less than 65 is going to be, now we need to calculate the z-score. So we're going to use this formula. Z is x minus mu over sigma, the standard deviation. So this is going to be the probability that z is less than x, which is 65, minus mu, that's 74, divided by the standard deviation of 6.8. So 65 minus 74 is negative 9. Negative 9 divided by 6.8 gives us negative 1.32. So now that we have the z-score, let's go to the negative z table to get the answer. So a z-value of negative 1.32 corresponds to an area of 0.09342. So what this means is that there is a 9.342% chance that if we select a student at random, that's going to be the probability that his score is less than 65. So this is the answer in the form of a percentage. To get that number, just keep in mind you need to multiply this by 100. Now let's move on to part B. By the way, for each of these problems, feel free to pause the video and try it yourself. If a sample of 50 students is selected at random, what is the probability that the mean exam score of this group is greater than 75? Go ahead and try. So this time n is not 1 but 50. So we're no longer dealing with a population distribution, but we're dealing with a sampling distribution. So we have x bar as the random variable instead of x. And the mean is going to be mu x bar. But the mean is still going to be 74. That's not going to change. So what do we need to do here? Well, first, we need to calculate the probability that the mean is greater than 75. So 75 is somewhere to the right of 74. And we're trying to calculate the area of the shaded region. So once again, we need to calculate z. When dealing with a sampling distribution, z is going to be x bar minus mu. If n is small, it's going to be mu x bar. But since n is large, mu x bar is the same as mu. So just keep that in mind. And then divided by the standard deviation over the square root of n. So this is going to be, well, first, to get the probability or the area to the right, it's going to be 1 minus the probability that x bar is less than 75. Because the z table, it gives us the area to the left. So we have to find the complement of that value. So now let's use this formula to get the z-score. So this is going to be 1 minus the probability that z is less than x bar being 75, minus the mean, mu, which is 74, over the standard deviation, which is 6.8, divided by the square root of n, and n is 50. So 75 minus 74, that's going to be 1. And 6.8 divided by the square root of 50, that's 0.961665. So 1 divided by that number is approximately 1.04 if you round it. So now we can go to the positive z table to get the area corresponding to this value. So this is going to be 1 minus. Now a z-score of 1.04 corresponds to an area. This is an area to the left, that's this region, of 0.85083. So just keep in mind this value corresponds to the shaded region in red. But when we use that number and subtract it from 1, we're going to get the area in blue, which is what we want. So the final answer is 0.14917. So what this means is that there's a 14.9% chance that if we select a sample of 50 students, the mean exam score is going to be greater than 75. Now let's move on to part C. What is the distribution for the mean exam score of 50 students? How can we write the distribution for the mean exam score? So because we're dealing with the mean, it's going to be x bar. And it is a normal distribution. And then we need to write the mean. And we also need to write the standard error, which is going to be sigma divided by the square root of n. So now, let's replace the mean. It's the mean of the sampling distribution, which is still going to be 74. And then sigma over square root of n, that's 6.8 divided by the square root of 50. And that is going to be 0.9617 if you round it. So that's how we can write the distribution for the mean exam scores of 50 students. Now let's move on to part D. Find the 80th percentile for the mean exam score of the 50 students. So going back to our normal distribution, we have a mean of 74, and at the bottom towards the left, this is the 0th percentile. The middle is the 50th percentile. At the end, that's the 100th percentile. So somewhere to the right of 74 is the 80th percentile. We need to calculate the mean score that corresponds to the 80th percentile. Now when dealing with the 80th percentile, the area to the left is going to be 0.80. So what we need to do is we need to use that to calculate the z-score. Because once we have the z-score, we could use this formula to calculate x bar. It's going to be, x bar is going to be the mean plus z times the standard error. So using the positive z-score table, an area of 0.8 corresponds to a z-score of 0.84. The actual area is like 0.79955, but that's the closest we can get to 0.8. So this is our z value, and we're going to plug it into this equation. And so the mean is 74, the z value is 0.84, and the standard error, which was 6.8 divided by the square root of 50, that's 0.9617. So this gives us a rounded answer of 74.81. So this is the mean exam score that corresponds to the 80th percentile. Number 2. The amount of carbs found in a snack bar produced by company XYZ follows a uniform distribution with a minimum of 21 grams to a maximum of 29 grams. A sample of 100 snack bars is taken for analysis. Part A. Write the distribution for the amount of carbs found in one snack bar and calculate the mean and standard deviation. So here's a question for you. For Part A, are we dealing with a population distribution or a sampling distribution? Well, we're dealing with one snack bar, so we're not dealing with a sampling distribution yet. We're dealing with a population distribution. Now, the shape of that population distribution is a uniform distribution. Now, we're given the minimum and the maximum value. The minimum value is 21. The maximum amount of carbs in a snack bar, that's 29. Now, to write the distribution for the amount of carbs, we could use these symbols. Since we're dealing with a population distribution, the random variable is x. It has the shape of a uniform distribution, and it varies between a and b. So for part A, we could say that the distribution is x, and then u, a to b, or 21 to 29. So that's the first part of part A. Now the second part, we need to calculate the mean and standard deviation. For a uniform distribution, the mean is simply the average of the minimum and the maximum values. So we're going to add 21 and 29 and then divide by 2. 21 plus 29 is 50. Half of 50 is 25. So the mean is 25. Now let's calculate the standard deviation. The formula that we need is b minus a divided by the square root of 12 for a uniform distribution. So that's 29 minus 21 divided by the square root of 12. 29 minus 21 is 8, and 8 divided by the square root of 12 will give us this number. So the standard deviation is 2.3094. So that's it for part A. Now, let's move on to part B. What is the distribution for the mean amount of 100 snack bars? What would you say? So now for part B, n is no longer 1. N is 100. So are we dealing with a population distribution or a sampling distribution? Since n is greater than 1, we're dealing with a sampling distribution, but a sampling distribution of the sample means. Now, what type of shape does the sampling distribution take? Would you say it has the shape of an exponential distribution, a uniform distribution, or a normal distribution? What would you say? Well, based on the central limit theorem, when n is greater than 30 or more, if n is sufficiently large enough, it doesn't matter what the shape of the population distribution is. In this case, the population distribution shape is uniform. But regardless of its shape, the sampling distribution will have the shape of a normal distribution when n is sufficiently large. So since we're dealing with a sampling distribution of the sample means, we're going to write x bar instead of x. And it takes on the shape of a normal distribution with the parameters the mean and the standard error. So we know that the mean is 25. Now to calculate the standard error, it's going to be the standard deviation divided by the square root of n, and n is 100. The square root of 100 is 10. So 2.3094 divided by 10, that's going to be 0.23094. So that's how we can write the distribution in part B. Now let's move on to part C. What is the probability that a single snack bar has between 24 grams and 26 grams of carbs? Go ahead and try that. So we know that n is 1. So this raises a question. Are we dealing with a population distribution or a sampling distribution. Since we're analyzing a single item, we're dealing with a population distribution, and it has the shape of a uniform distribution. So let's graph it. The minimum value is 21, the maximum value is 29. Now, how can we calculate the probability that the single snack bar X is between 24 and 26? To calculate the probability when dealing with a uniform distribution, you need to calculate the area under the curve in this range. So we need to calculate the area of this rectangle. But first, we need to find the y value of that distribution, which is f of x. Now, f of x is equal to 1 over b minus a. b is 29, a is 21. So f of x, the probability density function, is 1 over 8. So now we can calculate the probability that x is between 24 and 26. This is going to be the area of the rectangle, which is the base times the height. So the base is the difference between 26 and 24, which is 2. The height is basically, it's f of x, which is 1 over 8. So this becomes 2 over 8. 8 divided by 2 is 4, so 2 over 8 is 1 over 4. And 1 over 4 as a decimal is 0.25. So based on the shape of the uniform distribution, the probability that a single snack bar has between 24 and 26 grams of carbs is 0.25. Now, let's move on to part D. Find the probability that the mean amount of carbs in 100 snack bars is between 24.9 grams and 25.1 grams of carbs. So now we're dealing with the sampling distribution of the sample means, and it's going to have the shape of a normal distribution. So what we're going to do is calculate the probability that x bar, since we're dealing with means now, is between 24.9 and 25.1. So this is the probability that x bar is less than 25.1 minus the probability that x bar is less than 24.9. So now we need to calculate the z-score. So we're going to use this formula. It's going to be x bar minus the mean divided by the standard error. So this is going to be z is less than x bar, which is 25.1, minus the mean of 25 divided by. Now let's go ahead and get this value. So sigma over the square root of n, that's going to be 2.3094 divided by the square root of 100. And the square root of 100 is 10. So if we divide this number by 10, we're going to get 0.23094. So I'm just going to write that here. So this is the standard error of the mean. Now for this one, it's going to be z is less than 24.9 minus 25 over the same standard error. (25.1) minus 25, that's going to be 0.1. And 24.9 minus 25, that's negative 0.1. Now, 0.1 divided by 0.23094, that is 0.43. Negative 0.1 divided by the same number is going to be negative 0.43. So now, using the z-score table, if you go to the positive z-score table, 0.43 gives us an area of 0.664. This is the area to the left of 0.43. Now the area to the left of negative 0.43 for z, we need to go to the negative z table. So that's going to be 0.3336. So taking the difference of these two numbers, this will give us the probability that we're looking for, which is 0.3328. So this is the answer for part D. Now let's move on to part E. What is the distribution for the sum of carbs found in 100 snack bars? So this is another sampling distribution, but instead of dealing with the mean, we're dealing with a sum. It will still take on the shape of a normal distribution. Now the mean is going to be dealing with the sum of x, and the standard error is also dealing with the sum of x. So I changed the subscripts a bit. Now the mean value of the sum of all the carbs in 100 snack bars. If one snack bar has 25 grams of carbs, how many grams of carbs do you expect to be in 100 snack bars? It's going to be the mean times n, the sample size. So we have 25 grams in one snack bar times 100 snack bars. We should have a sum of 2,500 grams of carbs in 100 snack bars. Now to calculate the standard error associated with the sum, it's going to be the standard error that we see for the mean times n. So that's 0.23094 times 100. So the standard error in the sums is 23.094. So we can write our distribution like this. So the average sum of carbs in the 100 snack bars is 2,500 grams with a standard deviation of 23.094. Now I do need to make a correction because the sampling distribution is not associated with the mean, but rather it's associated with the sum of x. So just want to make that correction here. So this is the answer for part E. Now let's move on to part F. Find the probability that the sum of carbs, wait, what just happened there? Find a probability that the sum of carbs found in 100 snack bars is greater than 2540. So go ahead and try that. So the probability that the sum, okay, I really messed up there, that the sum of the x values is greater than 2540. We need to calculate the z-score. So we've seen formulas like this. Z is x minus mu over the standard deviation. In this case, this would be the standard error. For this one, it's going to be the sum of the x values minus the mean that's associated with the sum divided by the standard error of the sum of the x values. So the sum of the x values that we're concerned about here, that's 2540. Now the mean for the sum of the x values, that's 2500. And the standard error associated with the the sum of the x values is 23.094. So 2540 minus 2500, that's 40. 40 divided by 23.094, this is 1.73. So well, first we need to get the area to the right side, which is 1 minus PZ less than 1.73. That's the area to the left side. So now using the z-score table, a z-value of 1.73 corresponds to 0.95818. That's the area to the left. But to get the area to the right of 1.73, it's going to be 1 minus 0.95818. And so this gives us an answer of 0.04182. Number 3. The length of time that a car lasts follows an exponential distribution with a mean of 7 years. A sample of 40 cars is reviewed for analysis. Part A. What is the rate parameter and standard deviation? So what we know right now is that the population distribution has the shape of an exponential distribution. And we know that the mean is 7. With this information, what is the rate parameter and the standard deviation? For an exponential distribution, the standard deviation is the same as the mean. So it's also equal to 7. The rate parameter, lambda, is 1 over the mean. So it's 1 over 7. Now, we're going to take a sample of 40 cars. So n is 40. Now let's move on to part B. What is the distribution for the mean length of time that the 40 cars will last? So now we're dealing with a sample distribution, or rather a sampling distribution of the sample means. But how can we write this? So the random variable is going to be x bar instead of x. Since we're dealing with a sampling distribution and n is sufficiently large, it's going to take the shape of a normal distribution. And it's going to have the mean mu and the standard error sigma over the square root of n. Now let's calculate the standard error. The standard deviation is 7 and n is 40. So 7 divided by the square root of 40, that's going to give us a standard error of 1.1068. I'm going to write that here. So we can write our distribution as follows. So we have a mean of 7 and a standard error of 1.1068. So this right here is the answer to part B. Part C. What is the probability that the sample mean is less than 6.5 years? So the probability that x bar is less than 6.5 is going to be, first we need to calculate the z-score. So it's going to be x bar minus the mean divided by the standard error, which is the standard deviation divided by the square root of n. So this is the probability that z is less than x bar, which is 6.5, minus the mean of 7 over the standard error of 1.1068. 6.5 minus 7 is a negative 0.5, and if we divide that by 1.1068, we get a z value of negative 0.45. So now let's go to the negative z table. Negative 0.45 has an area value of 0.32636. So that is the probability that the sample mean will be less than 6.5 years. Now let's move on to part D. Determine the IQR for the mean length of time that the 40 cars will last. So the IQR, this stands for the interquartile range. It's the difference between the third quartile and the first quartile. Now keep in mind, we have a sampling distribution with the shape of a normal distribution. The mean value is 7. The mean corresponds to the 50th percentile. This is 0, this is 100. So Q1, that's going to be the 25th percentile. That should be in this region. The 75th percentile should be somewhere on the right side. So we need to calculate the x bar values that corresponds to Q1 and Q3. Let's call this x1 bar and x3 bar. X bar is equal to the mean plus the z-score times the standard error. So let's start with x bar 1. The mean is 7. We don't know what the z-score is, so we got to calculate z1. The area that corresponds to the 25th percentile is 0.25. So using the negative z table, an area of 0.25, it's going to have a z-score of approximately negative 0.675. Now let me explain how I got that value. So a z-score of negative 0.67 has an area value of 0.25143. It's close to 0.25, but not exactly. But a z-score of negative 0.68, it has a value of 0.24825. 0.25 is basically between those values, so that's why I chose an average of negative 0.67 and negative 0.68. So now that we have the z value that corresponds to the 25th percentile, we can plug it into that formula. So it's going to be 7 plus z, which is negative 0.675, and then times the standard error of 1.1068. So let's go ahead and find out what this equals to. So I got 6.253 if you round it. So this is the value of the first quartile. Now let's calculate the value of the third quartile. So the third quartile is the 75th percentile, which means the area to the left of that, that is this area here, that's going to be 0.75. So now, to determine the z-score that corresponds to it, we need the positive z table. And once again, we need to take the average of 0.67 and 0.68. So the z-score is going to be, instead of negative 0.675, it's positive 0.675. So using this formula again, we could say that x bar 3 for the third quartile, that's going to be the mean, mu, plus z of 0.675 times the standard error of 1.1068. So the third quartile is equal to 7.747. So now that we have the values of the first quartile and the third quartile, we can calculate the interquartile range using this formula. So let's take the difference of those two numbers. 7.747 minus 6.253. So this is going to be 1.494. So that's the interquartile range for part D. And that's basically it for this video. So now you understand the basic idea behind the central limit theorem, which states that if you take a sampling distribution of the means, and if the sample size is large enough, it's going to have the shape of a normal distribution, regardless of the shape of the population distribution. And you also know how to solve problems associated with the central limit theorem. So that's it for this video. Thanks again for watching, and if you found it to be helpful, don't forget to subscribe. Thanks again.